Okay, at the start of this question, we've got a full equation here. You can see it's a full equation, there's no electrons in it, and a half equation here. So this is one half of this equation. We've got to work out what the other half is. The key here is not to get too hung up and confused about the H pluses and waters, because this one has H plus and waters in it. And as you can see, that the waters are different and the H pluses are different. There's a good chance that this H2O2 and O2 will have some sort of H plus or water in it. So the H2O2 and the O2 are not in this half equation, so I'm going to put them down here. They must be in the other half equation. Now look at oxidation numbers. O2 is an element, so its oxidation number is 0, and oxygen in hydrogen peroxide, it's that exception to the rule, it's where oxygen is -1. So there are 2 oxygens going from -1 to 0, so in total there's 2 electrons being lost. So that gives us that bit there. We don't need to add any water because the oxygen's already balanced, but the hydrogens are not balanced. There's 2 hydrogens this side, so I put 2H plus on this side. That gives you the simplest half equation. So we're going to use this equation next for the redox titration. So let's copy that across there. So in this one then, what we have here is a sample of hydrogen peroxide, 25 centimeters cubed. So it's a concentrated sample, and it has been diluted into 250 centimeter cubed volumetric flask. So the difference being made up of water. And then each time I do a titration, confusingly, they take a 25 sample from the diluted one. Okay, so it's 225s to make it a bit confusing. They go on to say then that the potassium manganate being the burette, and the average titra to get to the end point is 23.45. So we've got to work out how many moles are coming out of the burette each time. So divide that volume by 1,000 times by the concentration of the potassium manganate, and that gives me that number of moles of potassium manganate. Then looking at the equation, I know how many manganate ions there are, but I'm trying to work out about hydrogen peroxide. It's a 2 to 5 ratio, so it's 2.5 times more moles of hydrogen peroxide in each titration. So I'm going to take my previous answer and I'm going to times it by 2.5 to get that number of moles of hydrogen peroxide. And that's each time you do the titration, so that's in that 25 centimeter cube there. I want to know how much, so I'm working backwards, how many moles there are in the stock sample of 250. So obviously 25 goes into 250 10 times, so I'm going to times my moles here by 10. Get that number of moles of hydrogen peroxide. Now, what I'm trying to get to is the concentration in this original sample. The number of moles that are in here will be the same as the number of moles in here. It's just been more diluted, but there's the same number of moles of hydrogen peroxide. So I know how many moles of hydrogen peroxide in there. I know its volume was 25, so I could work out its concentration. Take the moles, divide by the volume, make sure it's in dm cubed first. That gives me the answer in moles per dm cubed. If I want it in grams per dm cubed, as the question has asked, I've just got to times it by the molar mass, which for hydrogen peroxide is 34. So take that, times by 34, and I get 15.9 grams per dm cubed. The second part asks what volume of gas is measured at room temperature and pressure during the titration. You can see the oxygen, for every 2 manganate ions that react, you get again 5 oxygens, so it's another 5 to 2 ratio. So I'm taking this number of moles here and I'm times it by 2.5 again like this to get that number of moles there, and then see what volume that is. I times the volume, times the moles by 24, so I get that number of dm cubes.